Most people believe the first sign of danger from Etna will be a pillar of ash in the sky. The terrifying truth is, the first sign will be the ocean disappearing from the horizon. The new rhythmic tremors spiking under Etna are not a precursor to a lava flow. They are the sound of the volcano's unstable flank losing its final point of friction with the bedrock below. Geologists now understand this sound is not a warning of what is coming out of the crater, but of what is about to slide into the sea. What makes this tremor the point of no return for the flank collapse? And how could a silent slip on a volcano in Italy send a devastating wall of water to the coasts of Africa and Greece? Mount Etna stands as Europe's tallest and most active volcano, a colossus rising 3,329 meters above sea level, dominating Sicily's eastern coastline. But this familiar landmark hides a catastrophic potential that scientists have only recently begun to fully comprehend. Etna's origins stretch back approximately 500,000 years, beginning as a submarine volcano before emerging from the Mediterranean Sea through countless eruptions. This is not just any volcano, it is classified as a stratovolcano, built layer upon layer of hardened lava, pumice, and volcanic ash. Unlike the shield volcanoes of Hawaii with their gently sloping sides, Etna's steep profile creates inherent instability, a geological time bomb that has been ticking for millennia. What makes Etna particularly unusual is its complex tectonic setting. The volcano sits at the collision point between the African and Eurasian plates, and it also rests above a geological feature known as the Ionian Slab. That subducting oceanic plate generates magma that fuels Etna's frequent eruptions. More critically, it has caused the entire eastern flank of the volcano to slide steadily toward the Ionian Sea at rates of 2 to 3 centimeters per year. A seemingly insignificant movement that masks catastrophic potential. Ancient Romans called this volcano Etna, believing it housed the forge of Vulcan, the god of fire, and the prison of the monster Typhon. Their myths reflected a fundamental truth. Etna has always been dangerous. Historical records document over 200 major eruptions in the last 3,500 years, with the most destructive occurring in 1669 when lava flows destroyed parts of Catania and killed an estimated 20,000 people. But these surface eruptions aren't Etna's most terrifying capability. Geological evidence reveals something far more ominous. Approximately 8,000 years ago, a massive section of Etna's eastern flank catastrophically collapsed into the Mediterranean. This was not a gentle slumping, but a violent submarine landslide that displaced enough water to generate a mega tsunami. Sediment cores taken from the Mediterranean seafloor contain layers of volcanic debris that could only have been deposited by massive tsunami waves. These deposits extend as far as the eastern Mediterranean coastlines of Greece, Libya, and Egypt. They are evidence of a tsunami that would have devastated ancient coastal settlements. The scientific implications are clear. What happened before can happen again. Worryingly, the geological conditions today are remarkably similar to those that preceded the ancient collapse. Recent underwater mapping reveals another disturbing detail. The unstable eastern flank does not end at the shoreline. It continues underwater for nearly 20 kilometers, meaning a much larger portion of the volcano is unstable than previously believed. Estimates suggest as much as 35 cubic kilometers of volcanic material, roughly 8 times the volume of Manhattan, could be involved in a future collapse. Core samples from the seafloor below Etna's eastern flank show evidence of gradual deformation and previous smaller collapses. Radiocarbon dating indicates these events occur cyclically, with a major displacement approximately every few thousand years. By this timeline, we are overdue for the next major event. What's particularly concerning is that the volume, of unstable material has grown substantially larger since the last collapse. Each eruption adds more weight to the unstable flank, while magmatic intrusions underneath create zones of weakness. It's the geological equivalent of continuously adding bricks to an already leaning tower. Perhaps most troubling is the discovery of submarine fault lines running parallel to the coast, evidence of a deep-seated detachment surface that could allow the entire flank to move as a cohesive unit rather than breaking apart. This means that when failure occurs, it won't be gradual but catastrophic, precisely the conditions needed to generate a tsunami. While Etna's history reveals its catastrophic potential, it is current monitoring data that has volcanologists increasingly alarmed. Since the early 2000s, a sophisticated network of GPS stations, tilt meters, satellite, interferometry, and ocean bottom seismometers has tracked the volcano's movements with unprecedented precision. The data paints a disturbing picture. The eastern flank's movement toward the sea, once steady at 2 to 3 centimeters per year, has accelerated to nearly 4 centimeters per year in some areas. More concerning, this movement is not uniform. Certain sections are moving faster than others, creating tension zones where sudden failures are most likely. This acceleration coincides with increased seismic activity along the Pernicana-Provenzana fault system, a 20-kilometer network of fractures that essentially acts as the northern boundary of the unstable flank. Since 2018, this fault system has produced over 300 earthquakes exceeding magnitude 2.5, a 60% increase from the previous decade. The movement pattern follows what geologists call stick-slip behavior, periods of tension build-up followed by sudden releases. Each slip event temporarily relieves pressure before tension begins accumulating again. This pattern is remarkably similar to what occurs before major landslides worldwide. Ocean bottom pressure sensors deployed off Sicily's eastern coast have detected another ominous sign. The seafloor itself is deforming. As Etna's flank pushes seaward, it is compressing the underwater sediments, causing them to bulge upward in some areas and sink in others. These deformations create the perfect launching pad for a tsunami if rapid failure occurs. Satellite thermal imagery has identified another warning sign. Areas along the failure plane are showing elevated temperatures. This heating occurs when rock surfaces grind against each other, converting mechanical energy to heat. The temperature anomalies align with the regions producing the new rhythmic tremors. Recent underwater surveys using autonomous vehicles have revealed extensive networks of gas vents along the submarine portion of the flank. These vents release pressurized gases that can reduce friction between rock layers, essentially creating a natural lubricant that makes catastrophic sliding more likely. The regular eruptions from Etna's summit craters, while spectacular, are not the primary concern. It is the so-called silent flank eruptions that pose the greatest danger. These occur when magma intrudes laterally into the unstable flank, further weakening its structural integrity. The 2018 eruption opened fissures directly within the unstable zone, an event that accelerated the eastward movement rate by nearly 30% for several months afterward. Particularly troubling is the recent appearance of new fumaroles, vents releasing volcanic gases along the coastline itself. These indicate that magma is penetrating deeper into the flank than previously observed, potentially creating new zones of weakness precisely where structural integrity is most critical. Gravitational surveys conducted in 2021 detected another concerning development: voids forming within the volcanic edifice. These cavities likely result from magma withdrawing after intrusion events, leaving unsupported spaces that can collapse suddenly. Several of these voids align with the boundaries of the unstable flank. The Mediterranean Sea itself plays a role in this dangerous equation. During winter storms, water pressure against the submarine portion of the flank increases substantially. Following particularly violent Mediterranean storms, GPS stations consistently record brief acceleration in the flank's movement, evidence that even natural weather patterns are pushing this system toward failure. Perhaps most alarming is what happened in 2020, when a previously unknown fault suddenly activated beneath the village of Santa Venerina. That fault was not on any geological maps, and it produced a swarm of over 40 earthquakes in just 72 hours. Analysis revealed it connects directly to the deeper detachment surface beneath the entire unstable flank. It was a stark reminder that our understanding of Etna's fault network remains incomplete. The most disturbing development came just 3 months ago. Seismic stations across eastern Sicily began detecting something unprecedented: rhythmic tremors emanating from deep beneath Etna's eastern flank. Unlike typical volcanic tremors, which produce chaotic seismic signatures, these pulses occur with mechanical regularity, exactly every 47 seconds. Dr. Elena Romano of Italy's National Institute of Geophysics and Volcanology describes it as the seismic equivalent of a ticking clock. Her team's analysis reveals these tremors originate precisely along the main detachment surface, approximately 5 kilometers beneath the volcano's eastern slope, exactly where catastrophic failure would begin. The tremor's waveform characteristics match what geologists call slow slip events, the seismic signature of enormous rock masses beginning to move against each other. Similar patterns preceded major landslides in Alaska, Norway, and Japan. In each of those cases, the rhythmic tremors began weeks to months before catastrophic failure. What makes these tremors particularly concerning is their amplitude. The strength of the seismic signal has steadily increased by approximately 4% each week since they began. This progressive strengthening indicates the failure process is accelerating rather than stabilizing. Satellite interferometry, which can detect ground movement with millimeter precision, shows something equally alarming. The entire eastern flank is now moving as a coherent unit rather than separate sections. This change in behavior suggests the detachment surface has become fully developed, allowing the entire flank to slide as one massive block, precisely the condition needed for a tsunami-generating collapse. Ocean bottom seismometers deployed off Sicily's coast have detected another disturbing phenomenon: microseismic events occurring in sequence, starting inland and propagating toward the sea. This pattern suggests that strain is being transferred seaward, potentially setting up a zipper-like failure that could begin inland and rapidly accelerate as it reaches the coast. Laser scanning of key fault escarpments reveals fresh surface ruptures and new tension cracks forming parallel to the coastline. Some of these cracks have opened more than 30 centimeters in just the past year, visible evidence of the enormous stresses building within the volcano's flank. Perhaps most concerning is the detection of harmonic tremor swarms, bursts of rhythmic seismic activity that occur when fluids move through rock fractures. These swarms have become increasingly common along the submarine portion of the flank, suggesting that seawater is penetrating deeper into the failure zone. This infiltration further reduces friction along potential slide planes, essentially priming the system for catastrophic failure. Continuous GPS monitoring shows another troubling pattern. The unstable flank now exhibits distinct daily movement cycles, with maximum displacement occurring during low tides. This tidal correlation indicates the flank has become so unstable that even minor changes in sea level can influence its movement. The most alarming development came just weeks ago when researchers detected methane emissions from seafloor vents that had been dormant for decades. This sudden activation indicates that the subsurface fracture network is expanding, creating new pathways for gas to escape. The fracture expansion is direct evidence that the internal structure of the flank continues to deteriorate. Underwater drones equipped with high-resolution sonar have mapped previously unknown submarine scarps, underwater cliffs created by previous smaller landslides. These scarps have become increasingly unstable, with fresh debris accumulating at their bases. Some scarps now overhang by more than 2 meters, creating zones primed for imminent collapse. Geochemical analysis of groundwater from wells along the eastern flank shows increasing concentrations of magmatic gases, particularly carbon dioxide and helium-3. These gases can only reach the surface through newly formed fractures, providing chemical evidence that the internal fragmentation of the flank is accelerating. Historical analysis reveals a disturbing precedent. In 1918, before a significant earthquake damaged several coastal villages, observers reported unusual water disturbances offshore and rhythmic ground vibrations. The descriptions match almost exactly what monitoring equipment is detecting today. Thermal imaging conducted by research aircraft has identified linear heat anomalies extending from Etna's summit to the coastline. These thermal patterns align perfectly with the deeper detachment surface and indicate that friction along this plane is generating significant heat, a clear sign that massive rock volumes are already in motion beneath the surface. The tremors themselves show another worrying characteristic. They are no longer confined to deep sections of the flank, but have migrated progressively upward and eastward over recent weeks. This migration pattern suggests the failure zone is expanding toward the coast, potentially setting the stage for the submarine portion to fail catastrophically. Computer models incorporating all these data points yield a sobering conclusion. The probability of a major flank collapse has increased from less than 2% annually to nearly 5%, a significant jump in geological risk assessment. While that might seem small, it represents a dramatic escalation for a natural hazard of this magnitude. The most chilling aspect of these new rhythmic tremors is their resemblance to seismic patterns recorded before the 1888 collapse of Ritter Island volcano in Papua New Guinea. In that event, nearly half the volcanic island slid into the ocean, and that collapse generated a tsunami over 15 meters high that devastated coastlines more than 600 kilometers away. The pre-collapse seismic signature recorded by colonial German scientists matches almost exactly what we are now detecting beneath Etna. If a major flank collapse occurs, the tsunami threat would be unprecedented in modern European history. Wave propagation models indicate that a collapse involving just 1/3 of the unstable flank would generate tsunami waves exceeding 10 meters along Sicilian and Calabrian coastlines, arriving within 15 to 20 minutes of the collapse. Greece, Malta, Libya, and even Egypt's northern coast would face waves of 3 to 5 meters, arriving within 1 to 2 hours. The crowded Mediterranean coastlines, with their ancient ports and densely populated resort areas, present an evacuation nightmare. Unlike Pacific tsunami zones with extensive warning systems, many Mediterranean coastal towns have no tsunami awareness programs or evacuation routes. Most devastating of all, the first sign for coastal communities would not be a volcanic explosion, but the sudden, mysterious recession of the sea as the initial tsunami wave draws water away from shorelines. This phenomenon, which precedes all major tsunamis, would likely draw curious onlookers to exposed seafloor, placing them at maximum risk when the wave returns minutes later. As monitoring stations continue to record these ominous rhythmic tremors, the scientific consensus is shifting from if to when regarding a major flank collapse. The unsettling question is whether we will recognize the final warning signs in time to evacuate vulnerable coastlines. With each passing day, as the tremors continue their mechanical precision beneath Europe's largest volcano, we face an uncomfortable truth. Nature has already set events in motion that we cannot stop. We can only hope to detect the final acceleration in time to save lives. The rhythmic tremors beneath Etna are not just scientific curiosities, they are urgent warnings we cannot afford to ignore. If you found this analysis eye-opening, help spread awareness by sharing this Earth Attacks video with coastal communities around the Mediterranean. Remember, in a flank collapse scenario, every minute of warning could save thousands of lives. Subscribe now for continuing coverage as we monitor this developing situation, and visit our website for evacuation resources and live seismic updates. Together, we can ensure that when Etna's eastern flank finally fails, it will not catch us unprepared.